Okay. Okay, this lecture is about entropies and symmetries. So I have talked about symmetries. I have talked about these two algebras for the same region that are related to symmetries. And then now I want to talk about entropies in this context and how they can be used as order parameters for symmetries. Well, the first thing that if you want to have an order parameter, we have these two algebras. Here there are the additional non-local operators. So typically people will take these operators, these non-local operators, and evaluate expectation values in the vacuum and do some limits, whatever, and say, well, this is some phase or other phase that according to the behavior of these expectation values. I want to do something a little bit different, not much different, but a little bit different, that because here there are infinitely many representatives of a non-local operator. It can be thin, it can be fat, the non-local operator. So I would like to choose something that depends only on the vacuum and the region, and the topology and the geometry of the region. You can do that. For example, if you have a non-local operator A, there is a way to choose a unique one that belongs to the region and has some special properties that only depend on the vacuum. For example, there is something called the Tomita-Takesaki reflection of this algebra. Given an algebra and the vacuum state, let's say, you can produce some anti-unitary operator, and you could ask that this is equal to A. So this fixes A to be some particular, typically fat operator that accommodates itself to the size and geometry of the region. And then you can say, for example, a Wilson loop that has the geometry of the region R. And then one way would be to try to use this type of selected operators in this way. But I will follow a different route that is taking advantage that you have two algebras, just talking about entropies instead of expectation values of operators. This will give us some additional, some plus that is quite intriguing, and we will see. So I will talk about entropy. So typically, you will have the entropy of some region R. That is, you make the reduced density matrix. But this is usually, this is divergent in quantum field theory. It's not as well defined. Oh, rho. And then one thing that people can do in order to have something well defined is to take, for example, two regions, evaluate the mutual information. That is two regions, two algebras and one state. In this case, you evaluate this, AB plus SB minus SA union B. And this is finite and well-defined in quantum field theory, and axiomatically well-defined even. And there is another quantity that is very useful, is the relative entropy between two states in the same algebra now. And the fact that it appears these two things with this minus sign eliminates ultraviolet divergences. And again, this quantity, for example, the two states reduced to the same region is perfectly well defined in quantum field theory. And in fact, the mutual information can be seen as a relative entropy of rho AB with respect to rho A tensor product rho B. So it's a special kind of mutual information, of relative entropy. And the relative entropy is a very central quantity in quantum information theory, has a nice operational interpretation. It somehow tells us that to differentiate two different states, we have to, the probability of confounding the states after n measurements is proportional to e to the minus n, the relative entropy. It is also positive. Is greater than 0, is equal to 0, if and only if the two states are equal. So it's really a measure of distance, of distance between the two states. And it is also decreasing under channels, and in particular, if you make a partial trace and reduce your region, you will get a smaller relative entropy, meaning that the two states are less distinguishable because you have less operators. So then, now the problem is that we have two algebras, two different algebras, and one state that I will call it the vacuum. I will take the vacuum. I will put this vacuum on X, and this is just the expectation value of X, this notation. And then we have the other state. We only have one state, but two different algebras, and we want to have two states in the same algebra, right? So we need to evaluate, and one way to do that is to think in two states in the bigger algebra. Two states in the bigger algebra, one will be the vacuum, and the other will be a vacuum, but such a way that I will, by hand, put to 0 all the non-local operators. So I will say that, for example, if I have a non-local operator that is typically, see, this element of the bigger algebra is a combination of these non-local operators, and this is a local one, I will say that omega, this new state of A will be the vacuum evaluated in A0. And you could ask yourself if this is a state, still a state in the bigger algebra, and in fact it is, because one can think this is a combination of two things. One is a channel that maps the maximal algebra into the additive one, and then the vacuum state. So this is going to be the same as the vacuum composed with this channel. No, depending on the case. Here, yes, here is an operator that is supporting those regions, but it can be Wilson loop, for example. Okay. So, this is a special kind of channel that maps an algebra to a subalgebra and is the identity in the subalgebra. So it takes the element E applied to the AR is the identity. So, so it means that this state will have vacuum expectation values for all additive operators, but it will be 0 for non-local operators. So then we have now two states. One is the vacuum and one is this one in the bigger algebra. And then the thing is that one can evaluate then the relative entropy in the bigger algebra between omega, the vacuum, and omega composed with the conditional expectation. And this I will call the entropic order parameter. No, well, I will explain that later. Yes, we have to take some infrared limit or whatever, right?
But what is meant intuitively?
Intuitively is that it's the same as expectation value of these non-local operators in the sense that this thing will measure the statistics of the non-local operators because these two states are equal for the additive part. So the difference is just in the non-local operator. But it will measure it with the help of also of the full algebra of local operators or additive operators, and this will make some strange difference. Well, omega, yes, it's just the way people mathematically describe this state in an algebra. Here, yes, in principle, you can think in a lattice description, and then you have your density matrices, and then this is the usual relative entropy in the density matrix reduced to this algebra, right? Okay, so I take my density matrix and I write... Yeah, these two things in that case will be two density matrices, right? Okay. This channel, yeah, it will. So, for example, this thing, this channel, typically I will only talk about groups. In the case of a group, for example, you take EX, you want to eliminate all Churchill operators, and then EX is just 1 over G, a finite group, sum over G, G, X, G minus 1. So they will eliminate all non-local operators, or charge operators, and if X is some region and you have operators in different regions, just eliminate the global charge that is inside, right? So, okay. So it measures the statistics of the non-local operators, this quantity, so it's some kind of similar to expectation value of some preferred operator that adapts itself to the size of or the geometry of the region. And for example, one want to understand what are the possible values of this, and this, let me call it for short, is R, will go to 0 when the expectation values of the non-local operators are going to 0, right? Typically, because in that case, the two states are equal. In the other limit, one would like to understand what is the size of this in the limit where the expectation values go to the maximum value possible, and then one can do.
There's an expectation value
in the vacuum state. Yes, in the vacuum state. Yes, I can choose any states. That's it. Yeah, because I wanted to use it for all the parameters, right? Sorry, say it again.
Okay, sorry. So when you said that when are these two the same, right? And I thought, so suppose that I'm doing your symmetry example, and I pick some density matrix on a big system, and maybe there's like particle antiparticle pairs floating around, but I thought if there's no charges in the region that you're looking at, then those two will be the same.
Yeah, sure, but this can be applied to different setups. For example, if you have this broken symmetry phase, you have the non-local operator here as a possibility, and then the expectation value of this can be different from 0, right? If you have an unbroken symmetry phase, of course, this will always be 0, and this has no sense as such, but then you have to use this other one. Yeah. And then the expectation value of this is going to be the one that controls the size of the relative entropy. One can use convexity of relative entropy to show that this thing, when you have, for example, this conditional expectation type, then this is bounded above. Is bounded above by log of G. So it goes between 0 and log G. Is bounded by this. But it is possible to make a better upper bound because we have this AR, this complementarity diagram. Now I put something that is a conditional expectation that maps the big algebra to the small one, to the additive one. Again, I take commutants, and here I have the big algebra for the complementary region, and I have the additive algebra for the complementary region. And then for this other complementary region, I also have a conditional expectation, R prime. So in principle, there are two possible order parameters, one corresponding to this inclusion and one corresponding to this other inclusion. So I would like to take advantage of that to make a better upper bound here. Sorry?
Is the order of G, how do you get G from the input? The input is a state and an algebra?
Yeah, what I said is that I didn't want to, if you want, I can show you how you find this bound. But what I do here is just use this form of the conditional expectation here and use convexity of the relative entropy. This is a property, convexity of the relative, and under sum of the states, this is a sum of different states, right? Hi. Yeah, I'm thinking, I'm simplifying the possible relations between algebra and subalgebra that can be different. No, this applies to any case, to the Wilson loop case, to the two-ball case, to the single-ball case, depending on what type of symmetry you are looking at. Even for two intervals in 2 dimensions, it applies always. I'm just expressing this only in the case there is a group behind, right? To simplify, but I will go back to that. Well, I will also mention that. Well, for example, here I'm killing the charge operators. If the charge operator has discrete, this thing will be finite, even if unbounded, because it's unbounded. But if the charge operator is continuous, for example, if I take this other one and this other one is a U1 group, for example, then it's not well defined. It's infinite. No, this is infinite. One thing I want to mention is that in quantum field theory, because the algebras, this algebra is a factor, are factors, they don't have center, and also you have that the AR prime intersection AR hat is equal to the identity. The relative commutant, this is called the relative commutant, the algebra, the smaller algebra, the commutant inside R is the identity. So there is no operator in the bigger algebra that commutes with all AR, and this is because in order for a non-local operator to commute with everything local here, it would have to be in the boundary. In the boundary cannot be any operator, right? So you have this special property that is in the continuum. Of course, in the lattice, this will not hold, but in the continuum, it does hold, and in this case, the condition expectations, these mappings are completely unique, are completely defined already by the inclusion. In the lattice, you have to be careful that you maybe, depending on the choice of algebra, you maybe have several possible choices here. Then I will show that there is, you have this order parameter, and then we have also this other order parameter in R prime. So we have two order parameters, and we want to show that there is a relation between them. And this relation is coming from the usual property that the entropies for, people say the entropies for complementary regions are equal, but it's important that if you have a global pure state, the entropies of complementary algebras, commutant algebras, are the ones that are equal. So the entropy in an algebra A will be equal to the entropy in the algebra A prime. So this is for a pure state omega. This is the property that holds in this case. In this case, it's particularly important because, as we have seen, the algebra, the commutant of the algebra is not the algebra that you naturally will assign to the complementary region. So, let me show how this property that relates the two things, the two entropies, holds in a very simplified case. It can be demonstrated very generally in all situations, but in a very simplified case where you have this, the smallest, the simplest case will be these one-ball sectors with, you have your charge operators inside and the twist operators for the maximal algebra of the complementary region. So this is R, and this is R prime. And in order to do some calculations easily, I will suppose that we have a lattice, and there is here the charge operator in the lattice, so everything is finite. Everything is finite. So the relative entropy between two states can be written also as delta K, expectation value, minus delta S, where these are the entropies. This is the entropy of rho minus the entropy of sigma. And this is K is the logarithm, minus logarithm of the density matrix rho. So this is the entanglement Hamiltonian, K, this is entanglement Hamiltonian, or the modular Hamiltonian of this state here. And this is a variation of expectation values between the two states. This is trivially following from the definition of, it's just adding and subtracting the same term here, and you get that. So what I want to, I want to prove this thing for the special case where this tau form a group, and in order to use it the same for the complementary region, I will assume that this group is abelian, just for simplicity, but it can be done in any case. So as this is a group, we have that the trace, here you see that in our case, this state is invariant under the group, because of, by definition, it's invariant under the group. And then K, the logarithm of sigma, is invariant under the group. So we can say that trace of omega K is equal to trace of omega G, K, G minus 1. And this is equal to 1 over G, trace of the sum of G minus 1 over all the G's, G minus 1, G. Okay? And then this is equal to trace omega composed with a conditional expectation k, right? So it means the expectation value of the modular Hamiltonian is the same in the two states, so I am able here to eliminate this term. And with that, I get that the relative entropy in the maximal algebra of R between omega and omega composed with a conditional expectation is equal to the entropy, ordinary entropy of omega composed with conditional expectation minus the entropy of omega, both in the algebra, in the maximal algebra. So in this case, it's easy that you get a difference of entropy, just a difference of entropy. So now I will rewrite this. I will rewrite this entropy, this relative entropy. In the following way. So what I did here is just, let me see. We have this maximal algebra R. This was already before, and I only added this term and added this term and subtracted here. So I did nothing. And what I did, yes, what I did is that this R prime, this thing, I replace it by the entropy of the commutant, right? So I replace it, I use this property here. It's just using this property. A of R prime. No, A of R prime is the commutant of A maximal of R. Yeah? And then I will do the same again. This I will replace by S A maximal of R prime minus S of maximal of R prime of omega, and here omega composed with the conditional expectation, plus S of A R prime omega composed with conditional expectation R prime. So this, no, not yet. Yes, this here is maximal. So this I'm adding and subtracting here, minus S of A of R prime omega minus S of A maximal R omega composed with conditional expectation minus S of AR omega. Let me call this 1, this 2. So what I did is just added and subtracted this, and the other things are, I replace it by the commutant, and then here AR prime is this 1, and these 2 are these 2 here. It's a plus here, I think, right? It's a plus. Well, this thing now is in the maximal algebra of the commutant, right? And it's again, it's a difference of the entropy, so it's an abelian group, so it's the same stuff, and this is just minus the relative entropy in A maximal of R prime of omega composed, and omega composed with the dual conditional expectation. So I already made it appear here the other relative entropy. So we started with this, and here appeared the other one. And now we have to evaluate these two terms. And this term, in this term, we have to understand what is the maximal algebra of R prime. And here I'm thinking we have this ball. Let me see. Well, we have a ball here. Where I put it? Here. R prime maximal is the additive algebra outside plus the twist. I'm in the lattice, so this twist here is local, and then I can put some twist that goes through the ball, sharp, very sharp, that I cannot do in the continuum, but here I can do it. So I can say that this maximal algebra of R prime is the additive algebra of R prime, union some tau operators that are just these tau operators here. And then this conditional expectation, this object here, is invariant. This object kills the twist, So this object is 0 on all the twists, except the identity. And you can see easily that this state is, so this thing will be similar to A prime, AR prime, tensor product, the abelian algebra of the taus, right? Because it's this structure that the tau lives here, it commutes with the rest. And then this state is just factorizes. So this entropy here is the entropy of A additive R prime plus the entropy of the algebra of the taus. So this is the entropy of an abelian algebra, and it's not difficult to compute. You have to, in order, this is an abelian algebra written in a different way because the product of the tau give you another tau. So you have to select the projectors. The projectors on the different representation, let's say, and these projectors now behave as classical variables, independent classical variables. The expectation value of each of these is 0 for all taus except the identity. So as is one-dimensional representations, these give you PR expectation values equal to 1 over G. Right? So this entropy is log G. And here it comes the origin of this log G term. So this term, this will be killed by this, so this will be killed, and then you get a log G. And then we have to evaluate this one. By this one, you can say that this is the biggest algebra. The biggest algebra. Let me redraw like this. In the region R, with the different charges, and I have the different projectors for the different charge representations. And this is invariant under the group, so this density matrix lives here in the bigger algebra. But this is the same state now in the additive, in the additive algebra that is only uncharged operators. And this algebra is just block diagonal. It's here, it's the same. So these two states are the same, so this gives me 0. And from there, we get that the entropy, the two order parameters I put this in the other side. sum log G. So, and this is what we call the entropic certainty relation. Entropic certainty relation. So I will make some comments about this. The first is, as I mentioned, that this holds in any case. In every case, two-dimensional categories, whatever, we always hold. In general, the difference is that this number is replaced by log lambda, where lambda is called the index. Index of what? Is the index of the inclusion of the additive algebra inside the bigger algebra. And this index is the same for the commutant part, so for the complementary part. Is the same. If you want to see a proof of this very general for finite dimensional algebras, you can see the paper by Javier and Diego Pontello, and there is a proof of this, completely general. And if proofs in type 3 algebras also hold, and there is a paper by Hollands and another paper by Feng Shu, where they were able to prove this. So in general, is the index here, the index is the size of the group. The second commentary is that so this index is what I was saying yesterday, that these two inclusions that are of the same size, in the sense of they have the same, intuitively have the same number of non-local operators if the index is finite. Well, then why we call this entropic certainty relation? Because it's somehow, behind this is the uncertainty relations, because of the non-local operator of this, and this will not commute. So there is kind of uncertainty relation here. For example, if I have a group set 2, if I have set group set 2, let's say the square of the charge operator is equal to 1, and the square of the tau operator is equal to 1, and tau phi is equal to minus phi tau, a group set 2. Then I could use this non-commutativity to produce a uncertainty relation, as is usually done for operators. And what you get is that 1 minus the expectation value of tau square minus the expectation value of phi square is greater or equal than 0. So this tells you that if the expectation value of tau is going to 1, then better than the expectation value of phi goes to 0, typically uncertainty relation. But this does not prohibit that the two expectation values are very small. This doesn't tell you nothing about that. And here you have something that is an equality, not an inequality. And then, for example, if when this is going to log G, the other one is going to 0, and vice versa, right? So it cannot be the case that, so if one is very large, the other is small, and this somehow improves the uncertainty relation here, because if both were small here, both will be zero. Will be very zero. That is not correct. Something like that, yes. Perhaps the name is not well, because it's kind of uncertainty relation, but with certainty. Yes, exactly. Yeah. And why is that this is kind of improved in this sense? The reason is that you are adding to these operators, these non-local operators, also the additive algebra. The additive algebra, the full additive algebra. So it means that the additive algebra allows you to choose somehow the best ones of those there in such a way that this holds. This holds for any pure state, not necessarily the vacuum. It's the same for any pure state, because I use this property of the pure state and the relation between entropies of complementary algebras. But for example, for impure state, this will be less, because this will be reduced for an impure state. Global state. Well, this uncertainty relation has also an interesting application, is that allows us to somehow understand how to compute these things, at least approximately, by using some subset of operators that we know better. For example, because of monotonicity. Suppose I have this, suppose I have some particular set of phi operators and some particular set of tau operators that close an algebra between themselves. It can be an abelian algebra, whatever. And then what I can do is just, because of monotonicity, compute this thing just in the algebra of charge operators, and this will be less or equal than the entropy, than the order parameter I want to compute. And this, by the certainty relation, I can replace by log G minus the other one. And then this, again, by monotonicity, I can write an inequality So if you understand the expectation values of some set of charge operators and some set of twist operators, then you can, these are in general very simple things to compute. If this is a finite number and have an abelian algebra or whatever, these are very simple to compute. Then you can sandwich this relative entropy and have a calculation. What happens for continuous groups? For continuous group, as I mentioned, this number is going to be infinity, but only the algebra that kills a discrete set of operators is going to have a finite entanglement relative entropy. So what one expects about these order parameters, this type of order parameters, for example, the case of 2 balls, then we have this operator, and then you have the twist. If this distance is very small, so let me call epsilon, if this distance is very small, the relative entropy, let me call R to the 2 balls and R prime the outside. The relative entropy of the 2 balls will go to the maximal value because the correlation function is the maximal one, while the one of the outside part, because of the twist is pinched here, the expectation value goes to 0, and then it goes to 0. And the opposite case, because the correlation function goes to 0 to infinity, then this will go to 0, while the other one will go to maximal value. This is related also to what I said the other day, that in the case of epsilon going to 0, you can choose these things in the boundary. You have to do it with some special choices, such a way that expectation, let's say, is a unitary operator, such a way that this thing goes to the identity. Okay, so let me focus on this case, the case of the 2 balls. How much time do you have? Sorry? 45 minutes. Okay. So one thing that in this case of, we have now a theory, we have 2 balls, and we have the neutral part of the algebra is the additive algebra, and then we have this non-local operator, and the twist is the other non-local operator. And then one can see that this relative entropy in R, so in the 2 balls, is using some property of relative entropy that is calling the conditional expectation property. That I will not talk about because of a reason of time, but one can see that this thing is interesting, that is the same as the mutual information in the theory with charges between the 2 balls, minus the mutual information in the theory without charges in the 2 balls. So in this case, in this particular case, this order parameter is just a difference between mutual informations in 2 different theories. This is the one that completes this thing with local charges. And then one can say that one can think of this. One important thing is that the mutual information can be used as a way to get a well-defined notion of entropy for a single region. So this is, for example, we take a ball, and we take some distance here, epsilon, and then, let me call AB. This mutual information is the entropy of A plus the entropy of B minus the entropy of AB. And this can be thought as a regularization of the entropy of A. Why? Because suppose you have a lattice and everything is pure, epsilon goes to 0, this will be, entropy of AB will be 0, entropy of A will be equal to AB. So this mutual information in that limit, of course it diverges in that limit when epsilon goes to 0 because of a lot of correlations. But one can say that this is, so we can define a regularized entropy of A, let's say, to be this thing divided by 2, because it appears twice in the mutual information when these touch each other. So this is a very natural way to talk about entropy of one region in a regularization. Notice that this thing is well-defined and perfectly well-defined for any epsilon. So in fact, this thing, as expansion in epsilon, has the same structure as the usual expansion of the entropy in terms of divergences, area term, etc., right? So then in this limit, when we go to this formula, when we make epsilon go to 0, we know that this is going to be log G. This is going to be log G. So it means that the regularized entropy of F minus the regularized entropy of O is equal to log G divided by 2. So it means that there is a difference between the entropy, the regularized entropy of the theory with charges and the one without charges. And this number that appears here is in fact a topological thing. Why? Because if I have now a region that have holes, I have several pieces, several different pieces, and very many holes. You can go through this calculation and then make this regularization thing here and everywhere, and you get a contribution for each of the boundaries that is exactly the same. So this thing is going to be this multiplied by the number of boundaries of your region. So it's really a form of topological entropy, topological contribution to the entropy. I do not know if people will call this, well, let me make some remarks here. One thing is that let us think now that we have a gap theory, a gap theory, and compute the entropy of some ball in this way, with this regularized entropy. And then, but you can take a regularization epsilon, right? And if the epsilon is bigger than the gap, the mutual information is going to be 0. Because exponentially small, because there is no correlation between the inside and the outside. And then when you close epsilon, you can get something. In typically, let us think in 2 + 1 dimensions. The mutual information will go to something that is area, area over epsilon, some number here, typically area terms, because you have local contributions everywhere, plus some term minus f, right? Well, this is the universal contribution. But this is not, if we're in a gap theory, this is not what we expect in general. Suppose now that you have a non-gap theory, a scalar field. And then I get some area term, some f constant, exactly the same. But suppose now that I change the ultraviolet thing of the theory by some interaction, whatever, I still have a scalar field in the infrared. When I cross the scale of where the masses appear, I expect the same f. The f doesn't change. Why is that? This is important because this is the way we expect that f will be a quantity that is universal in the infrared. Otherwise, if you change the ultraviolet with the same infrared and get a different number, it's not universal, right? So typically we expect that. And why we expect that? Because we expect that the contribution of short distance entanglement will be additive, and this will give you an area term, but will not be able to change the f term. This is the usual assumption, or that by which f is universal in the infrared. But here is happening something different. Here I mean, for example, for the O theory. For the O theory, one expects here in this situation, for a very massive case, for example, you have a scalar, and the other is the scalar quotiented by the group, and then you expect that E AB for the theory F goes to area over G over epsilon, and the other one goes to some number area over epsilon minus this log G. So it suddenly appeared in this theory you have a for epsilon greater than the gap is for both of them are zero, the mutual information for both of them, but for one of them when you cross the gap it appears a term that was not supposed to be there. And why is that? The reason that this argument fails is that this theory, the orbifold, this O or the neutral part, has long distance constraints that make the argument of locality and why the F cannot change make it fail. So this is somehow my definition of what is the topological contribution to the entanglement entropy is something that in the mutual information, in the deep infrared, you have a gap, something that makes, even if in the case that it is not gapped, if that changes, when you go to ultraviolet, I would say that this contribution is topological. I don't know if people will call this a topological theory. I would like to hear about that. So no, this is my definition, but people call it topological, this type of theory, or you don't understand what is it. It's just a neutral part of a scalar field or a massive fermion field. You don't call it a theory. That's it. Yeah. That's not allowed. Why? Okay. Well, this is then a different kind of topological theory. Yeah. Right. Exactly. The Hamiltonian is the same as always. It's the same as in both theories. I think that will not do the show because it will change the correlators, right? It will change the correlators. This is not changing any correlators. Yeah, because. Okay. But this is a quantum field theory. Well-defined, local, everything, but it's not the one that, but typically, of course, there's other topological contributions that come from this other type of theories that have high duality violations for cone-like regions, for cone-like these BF theories, where what happened there is that what happened when you have this epsilon. Yes. Yeah, well, I will talk about that. Okay. Yeah, Maxwell field in 2 plus 1 is exactly this. Yeah. You can do both. You can do both. Both have this. Yeah, well, in that case, what you get is something that instead of being a constant is a logarithm of epsilon. I will talk about this now. Yeah, some logarithmic term.
Yeah, but that is
No, no, it's a universal. It's a universal, new universal contribution that is logarithmical in the cutoff. Yeah, sure. It depends. My cutoff here is physical, no? It's physical, but it's a cutoff. Yeah. Yeah, yeah. For example, if you make a compactify, this will be the radius of compactification. So I will go through this. No, no, we are in 2+1. We are in 2+1. So it has the dimensions. So what is the case of the usual topological terms is the case that then you don't have any violations of Hug duality for balls. There is no such a thing. You can have violation of Hug duality for infinite cones, but you have these operators like the electric flux. This electric flux, such that in the topological limit of something like that, this flux have expectation value U1, but if you cut this into pieces, then the expectation value of each of the pieces is small, and then it means that there are very non-local correlations, and these non-local correlations are the ones that produce the violation of the usual argument that this does not appear. So it's interesting that this same type of contribution is the one that explains such one thing that was puzzling people some time ago, that is the fact that if I compute the entropy of the Maxwell field in 4 dimensions, this goes like an area term minus 16 over 31 log r over epsilon. And this number is not the one that people usually think. This is the A anomaly. This is not the A anomaly. The A anomaly is in fact equal to 45, yes. 45. 31 over 45. So it's different. And this you can check numerically, you can compute perfectly well that the Maxwell field doesn't have the logarithmic term, correct logarithmic term. And then the reason why this term appears is quite strange, is because topological contribution, if there are charges. If there are charges, what happens is that if this electric flux is smear in sizes higher than so my epsilon is higher than the size of the charges, then you have the constraints that the full electric flux is 0, and then the small pieces have a perimeter law, and then you get this number. So you get the infrared Maxwell field, but when you cross the scale of epsilon, these things have an area law instead of having a perimeter law, and then it changes. It changes to this one. So the thing that that corrects to the right anomaly term is a topological contribution that needs both electric charges and magnetic charges. Otherwise, you get the half of it. So it needs to be somehow complete or almost complete, because with only one electric charge or only one magnetic charge is enough. Otherwise, it's going to have some subleading constant term or something like that. But if it is complete, you get that. If it's not complete, you get the other number. Sorry? No, this is 4 plus 1.
3 plus 1.
Yeah. 3 plus 1. 3 plus 1. 3 plus 1. Yes.
How much what is it in 2 plus 1?
No, well, let me say here where is it?
It's also a logarithm there.
let me. So this SR. In the case of a spontaneous symmetry breaking, that is the case of the Maxwell field in 2 + 1 dimensions, what you get is that this SR is this SR is the difference between these two mutual information. Right? In this case, is the full scalar field, and here the Maxwell. So this is scalar, and this is Maxwell. The derivative of the scalar. Okay? So the relative entropy in that case goes like G d minus 2 over 2. The relative entropy, the difference between the two, goes like this, log lambda mu. This lambda is the size. So I'm here taking this is the radius, if you want. Oh, sorry. This G is just if you have a symmetry breaking of a continuous group, you have the number of Gauss bosons.
It's a number of Gauss.
Yeah.
It's a number.
Right. It's just a number. And this can be computed by just a scalar, this kind of scalar. And so in that case, you need that the charges of your theory are discrete, and this gives you the compactification here. And this is a relative entropy that kills the charges. The other one doesn't exist, and is unbounded because log G is unbounded because the group is continuous. Sorry. This is the space-time dimension. This is space-time dimension. So in fact, yes. In fact, in 2 dimensions, the derivative of the scalar has a similar term, but it's a log-log. It's a log-log. Well. So let me take the last part of the talk. I will not be able to show how you compute things using these bounds. So you got.
The topological theories have a feature which, in a sense, they are more than scaling variant. They're independent of the metric. The compactified scalar, which is the Gauss unknown, is not actually a control. It's a fixed point in some sense, but it's not truly scaling variant.
No.
The actions
Yeah.
So it's not dimensionless.
Right.
It would be dimensionless 1 + 1.
Exactly. Yeah.
So that, in that sense, is different. It's not. I mean, these terms do not have a topological origin.
No. This is not a topological origin. This is just this is what replaces the log G that I was putting here. Well, okay, you're saying that because I'm talking this as a topological order if you have a gap theory, because of this that changes when you cross the scale. But it's of the same origin as this one, right? It's the same origin. Well, I wanted to show some specific calculation of these things using the fact that you can bound the relative entropy up and lower bound with using expectation value of operators. Then in some situations, for example, spontaneous symmetry breaking of gauge theories or non-gauge theories, you can compute the expectation values of these operators using the path integral, and then you get some specific calculation and you get some results. In fact, in those cases, even both upper and lower bound can be computed to the same order in the exponential term, and they match this exponential, so you can be certain on how this relative entropy goes exponentially in this limit, just computing a kind of domain wall or instanton or semi-classically. And there are other cases we also could compute, for example, the Maxwell case, or with the same techniques. So let me then go through phases and order parameters. So one, I think, nice feature of this thing that depends now on the geometry of a region is that you can take a limit that is more natural for talking about renormalization group flow or talking about phases. It's not that you get much more than that, but it's somehow more natural, because people, for example, takes this Wilson loop that is very thin in one direction and very large in the other direction. Is not natural from the point of view of the renormalization group flow. What you want is to take something and scale everything together. And for example, if I have 2 balls, I will take 2 balls and then scale it, and the distance will scale also. Or the same for a loop. I will scale everything together. Let's say keeping the cross ratios invariant, keeping the conformal geometry invariant. So let me go through the description of what you find for the order. Well, and in this limit, so I will take this dilatation lambda going to infinity, for example, to go to infrared, or lambda going to 0 for the ultraviolet. So in the case of the 2 balls, one can study global symmetry, let's say, or zero form symmetry. And then, depending on how it behaves, as lambda goes to infinity, you can see what will happen. So you will have a conformal phase, where the relative entropies will depend on the cross ratios of the thing, because it's a conformal phase, and will be constant. So in this case, the relative entropy of R and the relative entropy of R prime do not saturate either to 0 or to log G, do not saturate, and depend on the conformal. This is trivial. One can think this is completely trivial. Then we have two phases, 2 dual phases. Sorry?
This would still be true even if there were relevant operators. When you say phase, it's just to me that you're talking about some stable phase.
Yeah.
Is that important for what you're saying?
This is going to for example, no, you mean if it is everywhere conformal. No, I mean only in the limit.
But it could be just a critical point. It would still be true.
If it is conformal, yes. Yeah. Okay. So, and then you have other phases that, according to how the thing moves, that one can say is a massive or gap phase, where this SR goes exponentially to 0, and SR prime, of course, goes to log G minus e to the minus 2 ml. M is the gap. And this is easy to see because in that case, this expands. It doesn't matter that it increases, but because the gap will suppress correlations exponentially. And the other dual phase is the broken symmetry phase. Where you have that SR goes as log G minus e to the minus 2 B, this increases with the volume. Oh, let me call it mu here in order not to confuse. So this goes like this. This in that case the twist expectation value goes exponentially fast to 0 with the volume. So this is why this goes to 0 with the volume, while this otherwise saturates. And you can even compute this quantity with a semi-classical calculation sometimes. So these somehow are dual to each other in this case. And you can also see easily how this grows with the volume, and this is because if you have, in this case, a ball, and you want to 2 balls, and you have charge operators, I'm taking some charge operators, and if the theory goes to some gap, then these charge operators are uncorrelated to each other. And then when you have a set of, I said that you can bound below the relative entropy by some subalgebra. Suppose you have a subalgebra of operators, charge operators, that is formed by the tensor product of many charge operators, and they are uncorrelated to each other, as happens when you have a gap. They are uncorrelated. Then you can compute, and then you can compute that this thing will go exponentially with the number of charge operators that you can put that are uncorrelated. So here, the number that I can put grows with the volume, and then this is the reason why this goes with the volume. Sorry? Tower? Ah, okay. You can do both things, say that these things are uncorrelated and they are small, or you can choose some special, very nice operator that is big here, and for example, with the path integral, you can do that and compute the thing. Okay, well, and the spontaneous symmetry breaking case is this one. The other relative entropy doesn't have sense because it's infinity. So, and then we go to gauge theories. So it's interesting that in this dilatation thing, what you expect in terms of operators is that your operators goes to, one of them, the twist goes, for example, here as exponentially small, have a volume law, and the other one goes to a constant law. And this is a constant law for one of them, goes to the volume law for the other because of this thing that you can put many of them uncorrelated that produces the volume law there, and exactly the same will happen for gauge theories. So you have a twist of, a Wilson loop order parameter and a Toff loop order parameter, and then depending on the behavior at infinity, you can say, well, these order parameters, these relative entropies do not saturate, in this case, they depend on the particular conformal geometry, and this is a conformal phase. In the other case, saturate either to 0 or either to log G. And in that case, saturate, they saturate independently of the geometry. Independently of the geometry, so all saturation doesn't matter. And we have still two possibilities. One is exponentially fast. These are the usual cases of confinement. And symmetry breaking, spontaneous symmetry breaking. Of course, here we can say that, for example, the Wilson loop goes like e to the minus area mu, and the top loop goes like log z minus e to the minus area mu, and the converse here, and of course this we cannot compute, but here in the spontaneous breaking we can compute even the coefficients. And the other possibility is that you get a power law, so saturate, but with a power law instead of, and this is, for example, the asymptotically free case. Well, what happens in that case? In that limit, what happens in the limit of small things in the what happen? Yeah, you compute as in kind of the computation is complicated, but you compute as in the Maxwell case, but the charge of the Wilson loop renormalizes and then give you the power law. That's it. Yeah. No, yeah, it's a log in the exponent because it's a log in the expectation value of the Wilson loop. So you have a power law here, and here also in the Coulomb phases. No, in QED. No, in Maxwell theory. No, in Maxwell theory it's a conformal phase. It's a conformal phase. So it depends on the cross ratio.
So if you take a circle, for instance, you get the perimeter part and you get the power law.
Well, here we are thinking in something that is not cutoff dependent, so it's something that is a number between 0 and 1 because it's a Wilson loop that is a unitary operator, and it doesn't change with scale in the Maxwell case. It doesn't change because it's the same thing, right?
If you compute that for a circle, I did that calculation.
For a circle, I don't understand. For a line.
For a Wilson loop.
Right.
With the shape of a circle.
Yeah.
I think he's talking about the subleading correction. I mean,
There's a power law in front.
like a correction in front of the exponential.
Right. It goes like e to the minus L, and in front of the exponential there is a power law.
Okay. You are thinking in a.
If you want, you can put it upstairs as a logarithm.
Okay. Okay. Well, and again, these cases can be understood. For example, the case. For example, let me think. This is a Wilson loop, and then I can draw many top loops that cross here. The number of them will grow with the area. And then what's happening in this, for example, the confinement case is that the area law comes from the fact that the dual operator, it has a constant law, so it doesn't, you can actually take it with, if you are in fat, you make it fat, crossing the confinement scale, then the top loop can be made approach to 1, the expectation value. So this, and also they are uncorrelated, and then you can get this area law because of that. But of course, this here is just a picture, and you can do this here more precisely. Okay, I think this is what I wanted to say, and I think my time is already. Okay.
Reconstructing theories from wave functions, you're sort of reconstructing theories from the sense of like global operators and the operator algebra. And so I guess I was wondering, do you think it's feasible to attempt to do a similar thing to what John talked about this morning, where you say, oh, here's the conditions that, you know, if I worked at a topological fixed point, right, here's the conditions on the operators that keep me, you know, in the TQFT, or here's the conditions of the operators somehow, you know, allowed in the CFT, and then actually attempt to search for, you know, say, all theories that satisfy those conditions?
Well, in general, all the, well, depends on what kind of, if you without thinking about the state, or you are thinking about the state, without thinking about the state, just the algebras, for example, this type of high duality violations, really, if you impose this high duality violation, then you have to, it already gives you something about the theory that you are looking for. It has to be, for example, gauge theory with something like that. The high duality violations of 2 balls, for example, you can impose that, but then, as we know, you can always think in a theory, build up from that without that. It will tell you that there is a symmetry in the theory. It will tell you that there is a global symmetry in the theory if you impose that. In the symmetry, this global symmetry it acts on the extended algebra that doesn't have this problem. And then there is these other cases with high duality violations on cones, or, for example, the case of a single ball in the symmetry breaking case, that those cases somehow imply that you have some kind of dynamical thing going on that produces this type of high duality violation. So it already tells you something about the dynamics. In the case of a single ball, it has to be a case of a symmetry breaking. Then, if you want to have more details, I think you typically you need the vacuum to say something more. You need some state to say something. For example, these entropies or whatever you want, right? But in a relativistic theory, what he was saying is somehow correct from the beginning, that the correlation functions inside a ball give you the full theory, and also you can, for example, the modular Hamiltonian for the half space already contains the extents of the energy density, and then it gives you the model somehow. Okay. But now, if you have the Virasoro algebra, you are giving me a lot of information. You're giving me the full. So not a global feature or thing, but the full thing. The Virasoro algebra is already a theory, right? And from that, for example, from some Virasoro algebra, you can construct many different kind of extensions, and in principle, they are uniquely defined by the Virasoro algebra. So all this information is inside that. Yeah, the single algebra, yes. But if you have the algebra and the vacuum, then, and you say this is the vacuum for this, then I think you can get everything. Yeah. Yes.
Several particular examples of regions, like the balls, two balls, cones. Is it clear that there are other topologies of regions?
Well, this is a nice question. We are trying to work on that. But for example, one thing that we think that is correct, and we have a kind of proof, still not completely rigorous, but is that you have something like this, whatever. So in this game, it's important the DHR theorem because it allows you to kill some Hug duality violations. And when you do that, some Hug duality, I mean the ones corresponding to disconnected regions. Once you have done that, you have a theory is complete in that sense. Many results follow. For example, that if you take two theories, two regions, and do the sum here, what is called the direct sum of the two topologies, just glue some ball here, then the sectors of this region is just the tensor product of the two. So you already know, if you know, for example, these two rings, the sectors will be the tensor product, and then also for this will be the tensor product.
And then in principle you can prove again that, but now not them. So that in principle tells you that knotted things do not contain more sectors
Yeah.
than the unknotted thing.
Yeah. So the knotted rings will have also abelian groups, but it could have some kind of statistics. Yeah.
That is consistent with the topological field theory. I mean, the article by the famous article by Edward Itten, basically it's the same.
Yeah, you can have. So, yeah, but restricted to abelian groups. So it's a kind of possibility that.
Yes, for in our paper, the sectors of complicated things he builds from the sectors of simple things. Yeah, by side, no? And so the point is that here we are trying to prove that for the local field theory, which is not so trivial, but in principle is consistent with the more complicated cases. Is what you expect. Although, yeah.
Yeah, but it could be the case that because in 2+1, every of these problems is already solved by DHR theorem, because all the sectors that you can imagine correspond to disconnected regions or shells. So it already kills any problem in 3 dimensions. Of course, not the ones on infinite regions. But in 4 dimensions, you have more topologies, and then I don't know how many topologies or things that you can put there.
Well, maybe it's,
Yeah. Yeah, that's all.
Apologies in article. And let's thank Horacio again. And please go everybody to the stairs.